Okay, so welcome everyone to the Friday afternoon session and also the last talk of the conference. So I'm very happy to introduce Abraham Ng from University of Wollongong, who will talk to us about K-theory for algebras associated with commuting Hilbert bimodules. So please.
Cool. Thanks for the introduction, Kevin. And thanks to David and Lisa for inviting me, total rando, to take the premier spot, the last one. And being the last speaker, I'll try my best to let you all go on a high and not leave on with a sour taste in your mouth of what would otherwise be a marvelous workshop. Okay, so this is joint work with Astrid and Hoof from the Victoria University of Wellington and Aidan Sims at the University of Wollongong. And I'll pop this up soon, so nothing important will be down here that you can't see. But I thought I'd intro by talking about stable finiteness a bit, which doesn't actually appear in the title, but it did appear in the abstract if you paid attention. But first things first, A is always going to be a C-star algebra. And we say that A is stably finite, henceforth SF, and I'll do a lot of these abbreviations. If there exists, so if there does not exist a partial isometry S in a tensor compacts such that S star is strictly less than S star S, right? And the nice thing about stable finiteness, well, actually, people care about stable finiteness for a whole bunch of reasons. People in classification care about them, about it. It's linked to AF embeddability, quasi-diagonality, and things like that. And generally, has some good permanence properties. So it's preserved under passing to a subalgebra. It's preserved under Morita equivalence. It's preserved under taking direct limits. But one thing it's generally poorly behaved with respect to is extensions, right? So if you have some extension, say some ideal I and some quotient B and an extension A, generally speaking, if I and B are stably finite, A isn't, right? Generally speaking. But there is a characterization of when if I and B are stably finite when A is. And this is a theorem due to Jack Spielberg in the 1980s. And true to I feel like it's a recurrent thing this conference, but he called it a lemma, but it really should be a theorem. Okay, so what does it say? Well, it says that if I and B are stably finite, then A is stably finite if and only if the kernel of I star, which is the map, so this is the inclusion I, if kernel of I star intersect the positive cone of the K0 group of I is 0. If this happens, then A is stably finite. Okay, so there's a characterization of stable finiteness of the extension based on this this property of I star. Okay, so the key takeaway here is that I star is important, and I guess take this away, if nothing else. And we'll come back to it. So now we're going to leave stable finiteness for a bit, and eventually it'll hopefully pop up again at the very end. But let me pop this up and kind of briefly give you an outline of what the talk will be. Okay, so there'll be 4 sections. Section 1, 4 boards. I'll talk a bit about Hilbert bimodules. Some people have already talked about them and the associated algebras. And I'll talk about this construction by Diaconou and Fletcher for what we call commuting Hilbert bimodules, HB. And then I'll talk a bit about the K-theory for these commuting, these algebras associating to these commuting Hilbert bimodules. And at the very end, I hopefully can tie it all together with some stable finiteness again, going full circle. Okay, so let's start with some Hilbert bimodules. So again, A is a C-star algebra. And what do we need? So we need X, which is actually, let me say AB. I got 2 C-star algebras, A and B. And X is a right a right module of A, and so we've got a right action by A. What else do we need? We need an inner product. So I guess plus an inner product that goes from x times x to A, and you can just think of it as a C-star algebra valued inner product. And it satisfies the things you'd expect an inner product would satisfy. For example, if you took the inner product of a vector with itself, you should expect it to be a positive element, 0 if and only if it's 0. You take it the other way around, you get the adjoint, like all that stuff, all that good stuff. But you also have, given you've got an action on the right, you also hope that you would have something like this. So if you had two vectors, xi and eta, and you act on eta with some element A of the C-star algebra, you should hope that you'd get this. Now these things are both elements of the algebra, okay? So that's the right action and the inner product. You also, in order to make it a bimodule, you need a left action by B. And so you also have a left action of B on X so here I won't explain too much, but by what you would call adjoinables. And throughout the talk again, I'll say what I think is the bare minimum you need to understand what the whole thing is going. Otherwise, if you know, you know. So we've got a left action, but it has to be somehow compatible with the inner product. And so you should hope that if you're acting, say, on the left by some B and B, on some zeta, some xi, and you take the inner product, then this should somehow, you should get the adjoint action on the other side. Okay, so pretty much what you would expect. Okay, if you have this, then you say then X is a BA Hilbert bimodule, and sometimes I'll put subscripts, B for the left action and A on the right action. Okay, sometimes I'll leave it out, sometimes I'll leave it in, depending on if it's useful. Right. An important example of this, of course, is the C-star algebra itself, and you act on the left and right by multiplication, your classic. So if I guess AAA is an AA Hilbert bimodule, we'll definitely use it. Okay, so now what I also hope to do is generally on the left of these boards, I'll give you some theory, and on the right, I'll have a running example, right? Hence Reg. So we'll talk to Reg from time to time. And our running example is going to be something like this. So we have a map T, which is going to be, I'm going to take it to be surjective just so it's easier. So a surjective local homeomorphism on, and a very nice space. So on a totally disconnected, what else do I need? Locally compact Hausdorff space omega. And again, if you know what I'm about to do, that's cool. If not, just know that we've got a local homeomorphism on omega. So this actually gives us what some people would call a topological graph, where you have kind of vertices, edges, a source map, and a range map. Okay. Again, if that doesn't mean much to you, that's fine. Okay, so in this setting, how do we get a bimodule from one of these things? Well, the first thing we need is a C-star algebra, and so we take our C-star algebra A to be continuous function C0 of omega. We also need an inner product, right? So you can define an inner product from, let's take the space CC of omega to the algebra A, which is C0 of omega. So how does this work? So if you had xi, eta, so this should be a function, right? It should be in C0 of omega. So say of y, this is going to be, what I want. So I want to somehow include the t. So I would have tx, all the x's for which tx equals y, and then take kind of what you would expect to be the inner product. Okay, so we've got an inner product. It's not yet complete. We also need some actions. So let's say I have a left action by some function f in A, applied to some xi, and say a right action by g, and this should give me, left action should be multiplication, and then the right action should encode my map T, okay? So what you can do then is you can complete the space of compactly supported functions on omega with respect to this inner product, right? Just take the norm to be like square of inner product with something with itself. And so let me denote this by E sub T is CC omega, and then I take the completion with respect to this inner product that I've just defined. Okay, so this is the an Hilbert bimodule, and it's like the classic graph bimodule you'd have associated to a topological graph. I think Diakonu and Katsura worked on these kinds of things, so due credit to them. Let me also just label this so I can refer to it later. Call it lambda sub T. Right, okay, so we've got a bimodule, and we want now also to have some algebras associated to them. So luckily for me, Camilla already defined Kunz-Pimsner algebras, and Yuhei mentioned C-star correspondence as well. So I'll be very quick about this. So what do I need? So I need a bimodule, and maybe this will infuriate lots of people, but I'm just going to call it a very special representation. Let me make sure I don't make any mistakes. So there exists a special rep of X in a C-star algebra, which I'm going to call O sub X. And a rep consists of one map, I'll call it J1, and this is a star hom, which goes from the algebra A into O of X. And then I'm going to have a second map, which takes the bimodule and puts that into O of X. And kind of this is somehow, compatible with the structure. And then also this condition that Camilla had on her slides, and I don't want to write out either, Kunz-Pimsner covariant. And this particular OX is like universal with respect to these two conditions. Okay, and we call OX the Kunz-Pimsner algebra of X. And again, kind of Pimsner and Katsura define this in slightly different ways. Okay, now we go back to Reg. And let's continue our example from here. So if you have this set up, you have this graph module, what's the algebra you get from it? Well, all right, so we had our a top graph lambda T, or you can just think of it as a local homeomorphism on some totally disconnected space. Then actually, the algebra of this graph is actually it's straight up just defined to be the Kunz-Pimsner algebra of this graph module. Okay. But not only that, this is also isomorphic to another algebra, C star G sub T, where G sub T is the so-called Diakonu-Renaud groupoid of this action, where you just take powers of T as an action of n on omega, right? And if you haven't seen this before, what this looks like is it contains triples of the form x, p minus q, y in omega cross z cross omega, such that t to the power p of x equals t to the power q of y, right? This makes a groupoid, and everyone and their mothers define groupoids by now. So you kind of have source and range, right? And you can put them together if they match. Okay, so if you know Kunz-Pimsner algebras, you actually know that you can define them as a quotient of something called a Toeplitz algebra. In any case, from that, that short exact sequence, you can get like a 6-term K-theory sequence. So I've written that out for you. It's called the Pimsner sequence. Hopefully you can all see that. But if you've got a bimodule X, which kind of has A on the left and on the right, then you can have the 6-term sequence in K-theory. K0 of A maps into K0 of A, maps into K0 of the Kunz-Pimsner algebra, maps down to K1 of A, to K1 of A, to K1 of the Kunz-Pimsner algebra. These maps here, but I've kind of like square brackets X, again, if you know, you know, somehow corresponds to taking the Kasparov product in KK with that bimodule. Otherwise, I'll use this, so we just keep this here. Okay, so we also can say some things about ideals, right? So you've got an algebra A. So what happens if your algebra A has an ideal? Can you say anything about that? Well, yes. So again, let's say X is a Hilbert bimodule, and say I in A is closed. Then we say I is X invariant if kind of acting on X on the right by I is contained in kind of the space you get from acting on X from the left. Sorry, the other way around. Acting on X on the right by I. Okay, so in that case, what you have is you get like a new bimodule, like a smaller one, right? X dot I, and then it's acted on the left and the right by I. And this also turns out to be a Hilbert bimodule. Okay? And this plays very nicely with the Kunz-Pimsner algebra. So this is a theorem by Fowler, Muley, and Rayburn, and also possibly by Katsura, but I found the first paper easier to read. If you have an X invariant ideal, is what is X invariant, then there exists a injective star arm that goes from the Kunz-Pimsner algebra of this into the Kunz-Pimsner algebra of the original. Okay, and it's kind of like it comes from where you'd think it gets, right? It's kind of induced by exactly just the inclusion of I into A and the inclusion of X dot I into X. Okay, so there's nothing super mysterious about that. Okay, but back to Reg. If kind of we're working with keep running with that, then what are some ideals? Well, the ideal we care about is if you had H subset of omega, which is, let's say for our purposes, let's say it's Clopin, so everything's really nice, and it's invariant under T. So both the image of H under T and the pre-image of H under T is contained in H. In this case, then we can take the ideal I to be just C0 of H, right? And, well, this is an ideal in C0 of omega, and this is our A. And this is exactly ET invariant. And kind of what's more, you might notice that, okay, if I had such a subset, such a really nice subset, then I would also have a new topological graph given by HH, and then again T restricted to H, and the identity, right? And then so from what we were doing before, I can construct a new module based on this. And I can call it E sub T restricted to H, right? And this again matches up very nicely. So a proposition that the module you get just from kind of acting on ET on the right with this is just basically the same as if you just did this directly. Okay? Again, nothing super dramatic yet. Okay. So now we get to commuting Hilbert bimodules. What do I mean by that? Let's first start off with something, again, basic. Let's say I had two bimodules this time. One a BA bimodule, and say one was an AC bimodule. Then what I can first do is I can take a tensor product. I can take a algebraic tensor product. And then I could say, if I wanted to notice that, okay, I've got a right action on this by A, a left action on this by A, and I kind of somehow want that to pass back and forth between my, over my tensor product, well, I can quotient out things of the form xi dot A tensor eta minus xi tensor A dot eta, right? Just kind of like the things that go back and forth, I just say, let's just identify them. Okay, and then I can complete this with respect to give myself more space. What I do is I kind of take the first inner product with the xi's, use that to act on my etas, and then just take the new inner product on the outside, and this ends up giving me a new bimodule, right? So this gives me a so-called balanced tensor product, x kind of the tensor O times with a subscript a, y, and this ends up being having a B action on the left and a C action on the right. Okay, again, the way you act is you just act this side, you just act on this component, act on this side, you act on this component, and so on. Okay, so now, so you can do this as long as the kind of the inside algebra is the same. Okay, so let's say now both of them are AA bimodules, right? So I can say then that, so I can say x1 is one bimodule and x2 is another. I say these commute if it kind of doesn't matter which way around I take the balanced tensor product. Like in general, this wouldn't be true, right? Because the left and right actions might be really different. The workshop's called kind of something with symmetry in it, and this is not quite the symmetry maybe that was intended, but this looks symmetrical to me, so that's my link. Okay, so hole in my prep. So continuing with my running example, now let's say instead of having one local homeomorphism on omega, I had two, T1 and T2, local homeo on omega, and let's say they commute. Right, so just straight up T1 composed with T2 is the same as T2 composed with T1. Again, for those of you who know, this would give me you could actually define a rank 2 topological graph, lambda T, kind of via these two, T1, T2. But in any case, I end up having, I can define a graph bimodule for T1, I can define a graph bimodule for T2, and they commute in exactly this way. Okay? ET1 tensor over C0 of omega, ET2, ET2, ET1. Okay, so that's the definition of commuting bimodules. And now I get to this stuff by Diacono and Fletcher. Really, Diacono was the first to kind of say you can do this, but it was a very short, terse paper. And Fletcher kind of filled in the details, generalized it a bit more, made sure it all works, and kind of I don't know, did more stuff, did more good stuff. Okay, so in this case, let's start exactly with two bimodules that commute. C-O-M-M, commute. And the first thing we can notice is that, well, I can get a Kunz-Pimsner algebra from one of these, right? So I could just say, let's look at OX1. It's an algebra, and so we know that given an algebra, AAA is a Hilbert bimodule. I can actually get kind of OX1, OX1, OX1 gives me a Hilbert bimodule. And what I could do, I could also say, okay, say I don't actually want all of this action. Let's restrict it down to A, because A actually lives inside OX1, right? So I could, by restricting the left action, get the same bimodule, but kind of the action on the left is by A now instead. Okay. And now, well, now I have something which has a left A action and something else that has a right A action, and I can take the tensor product between these two things. Okay. So I can take x2 balanced over A with OX1. And this ends up being an A OX1 bimodule, and let me just call this Y. Okay. So it's kind of like, in Fletcher's words, it's like an iteration. Okay. Now what Diacono and Fletcher actually did was, okay, so I've got this Y, which is kind of like an iteration of x1. You apply Kunz-Pimsner construction to the first one, and then you tensor in the other one. I can actually, well, they can actually extend this action of A on the left back to OX1. So it's like on the same, it has the same algebra on the left and the right. Okay, so you can extend the action of A that's currently on Y to OX1 on Y. And the way they do it is like, somehow you want to pull the action across the tensor product. They use all these clever factorization tricks. Let's just leave it at that. And so the point now is that you have an OX1 bimodule, and so you can take a Kunz-Pimsner algebra. So you can take O of Y, okay? And this OY isn't arbitrary. This ends up being isomorphic to, again, if you know, you know. If you don't know, that's fine. A Kunz-Pimsner-Nika algebra for a product system where the product system is given by kind of x1 tensor itself m times tensor x2 n times. This would give you a product system. Again, if you know, you know. If you don't, that's fine. Okay. Okay, and not only that, you can also this construction also plays well with ideals. I don't think they did this, or maybe they did and we couldn't find it, but we redid it anyway. So if you have an ideal which is both x1 and x2 invariant, then what happens is kind of these smaller bimodules, they also commute. And so you can apply the same construction to get a y, but this time it's a smaller y, right? yi. And I'm sorry if you can't see this, but you know I planned this already. I need the space. There is a canonical Starholm phi, which goes from the Kunz-Pimsner algebra of this thing to the big one. Okay? We don't actually know it's injective. We just know there is a Starholm for now. Okay, so again, let's go back to Reg, and we've got T1, T2 commuting local homeos on omega. So now, so let my y be precisely this thing where I take the graph module associated to T2, and I tensor this over C0 omega with the Kunz-Pimsner algebra of the graph module associated to T1. And so it turns out then, in this case, that OY is isomorphic to C star of GT, where GT is the Diaconou-Renaud groupoid for, well, now this action, right? Like T mn equals to T1 to the power m, T2 to the power n, and this like is an action of n2 on omega. Okay. So this ends up being isomorphic. You might be able to see it another way, but there is a paper by Carlson, Larson, Sims, and Vitadello which kind of looks at a whole bunch of these constructions and shows that they're the same. Okay, and then we had our ideal from before where you had an invariant, say T1, T2 invariant subset of omega, and we said I was C0 of H. Then it turns out that this plays very nicely with this thing here. So O, Y, I, mapping through phi to O, Y, and then this is by this isomorphic to C star GT. This turns out to be isomorphic to C star GT restricted to H. And then the map that goes here is like it's an honest inclusion actually. Okay, provided your H is invariant. This is an actual inclusion. And so finally, with like 15 odd minutes to spare, we've found an injection of something, some ideal into some bigger algebra, which brings us back to the intro, right? And yet we've also got this kind of commuting diagram, which shows that if I want to look at this map I, or particularly I want to look at I star, the map induced in K theory, I can also just study this phi instead. Okay? So that's what I want to do. So we want to understand ooh, it's bad understand. I star that goes from K0 of C star GT restricted to H to K0 of C star GT. And because of that commuting diagram over there, I can study, instead of I star, I can study this phi star. Okay? Right, and so what we want to do, right, if we went back to the intro, is we wanted to have a really good handle on I star in order to check something like this. Okay, a condition like this. And so one way to have a really good handle on a map is to find it in the middle of a commuting diagram with short exact sequences. Right, then basically you have a really good idea of what goes on, what's in the kernel, what's in the range, how things play with each other. Right, this gives you a really good grasp. And so that's what we're trying to do, which comes to the title of the talk. We want to be able to both compute the K theory of these kind of iterated Kunz-Pimsner algebras. So one short exact sequence would give you that. But we want it also to be kind of natural with respect to these ideal inclusions, right? Because then you can get like a really good grasp. And so our theorem was to exactly prove that you have something like this. I put stars in here, so I'll fill them soon, hopefully. So you've got exactly the phi star we want to understand between K0 of Kunz-Pimsner algebra of Yi down into K0 of the Kunz-Pimsner algebra of Y. And then on the left and right, we've got some things, okay? So that's kind of what we want to prove. Right, so how do we do that? We use a big ass diagram. And it kind of looks complicated, but actually it shouldn't be too hard to see what's going on. So basically, whenever you have a Hilbert bimodule, an AXA, you get a 6-term sequence, okay? What we have is we have 2 Hilbert bimodules, kind of x1, AA, and we also have this y, this iterated version, which is that OX1, OX1, okay? So this central sequence is just kind of the 5 terms from that 6-term sequence, but centered at K0 of OY, okay? And then the coefficient algebra should appear here and here, which is OX1, OX1, and then K1, OX1, OX1. So this thing from the middle is just that. But also, since OX1 is a Kunz-Pimsner algebra, it has its own sequence, right? This time kind of going upwards, you might say. And its coefficient algebra of x1 is A. So you've kind of got something going up, which is K0A, K0A. And here we kind of make this like big assumption because in our case, in our reg, it works. So in the case where you have the really nice, like an AF algebra or something, and in this case, the C0 of omega is AF, so you have K1 is 0 in this case. This would have been like a 6-term sequence as well, but then we kill the K1s, okay? Okay, and now in order to get that thing from this, we notice actually, so the map that goes from here to here, this is this 1 minus square brackets y map, and same thing here, going here. What's going on is like, essentially you're kind of like tensoring on x2. Essentially that's what you're doing. And so what happens down here is actually this is exactly kind of square brackets x2, square brackets x2, and same thing here. And then the hard work is to show that this thing actually commutes, okay? So these two things, you've got something that's x1 and then x2 and then x1, x2 and then x1. This just commutes because x1 and x2 commute. Same thing here. This thing is not too hard to show, let's just say that. And then this square here, which has these boundary maps, was like the bane of my existence for like a few months, okay? Because I didn't actually want to compute anything with these boundary maps. And so we ended up making another big ass diagram to show that this works, using naturality for various sequences, and we had this nice diagram that looks like an imperial star destroyer. If you read this paper, you'll notice which diagram is that. Okay. The upshot is we get this diagram and it works. And not only does it work, so this is my diagram for just A and x1 and x2. You kind of have another diagram outside of the board, which is for the ideal version of this, right? And you kind of have like a diagram sitting here outside of this board, and kind of with arrows going in, and it all commutes, okay? And so in order to go from this thing to, let's say, one of these rows, well, the first thing you can do is, okay, this map is surjective, and so this thing is going to be isomorphic to this. If I mod out the kernel of this map is the image of this map, so I get a co-kernel here. Same thing here, co-kernel of this map gives me something that's isomorphic this way. And then here I've got an injection, so if I want an isomorphism, I need to kind of restrict to the image of this, which is the kernel of this. So I can replace this thing here with kernel of this map and kernel of this map here, right? So now I have something where I can replace these things with like a co-kernel of this map and co-kernel of this map, and I end up with like a 5-term sequence now instead, okay? And when you've got a 5-term sequence, then you can again apply first iso theorem to kind of take a co-kernel over here to get an injective map on this side, and over here you take, again, a kernel, and you end up with a surjective map, and you end up with this short exact sequence down here, okay? And then the whole diagram works precisely because all of these contractions doesn't mess with the fact that everything commutes when I have the ideal board over here, all right? So, okay, so at the end of the day, we end up getting this. So what actually goes in these stars, I'll write out the maps for you, because actually they end up being quite nice, but kind of no context, sorry. So you can define a map. It's a block matrix map, 1 minus x1, 1 minus x2, that goes from k0 of a plus k0 of a into k0 of a. What does it do? Well, it just sends a pair fg to the sum under these maps. F plus 1 minus x2 g. That's one block matrix map. And then I have another block matrix map, B2, which is kind of the other way around, as it were, from k0 of a into k0 a plus k0 of a. And this one basically just applies, you start with an f, and then you just apply this map to the first, to get the first bit, and the second map to get the second bit. Okay, so you just have two maps that are fairly easy to describe, the block matrix maps. Okay, so what happens then is that what goes in here, after you do some isomorphisms, what goes in here is precisely the co-kernel of the first block matrix map. What goes in here is the kernel of the second block matrix map. It's really quite nice. And then the same thing's up here, but for kind of the ideal versions. Okay, so you really get like a really good grasp of this map, basically. Okay, so going back to our running example again. Okay, so if A is C0 of omega, then K0 of A in this case is just isomorphic to the compactly supported functions from omega to z, right? And then we can define a map actually, say Ti star, that goes from Cc omega z into Cc omega z. What does this do? Well, if you take a function, say h in here, and you evaluate it at some point y, kind of encodes t into it and looks at the preimages of t. Okay, so you can just define a map like this. And in our case, these kind of square brackets x1 and x2 maps are precisely just these Ti star maps. Okay, so there's a theorem, and call it folklore. And it seems like it's well known, but we couldn't find a reference, so we proved it anyway, and it took a lot of pages, but we don't really claim credit for the idea. So these square bracket xi maps between the K0 groups of A to Cc omega z, these are precisely these Ti star maps. Okay, so now basically in our context for our running example, the things we put into here are kind of these nice block matrix maps, and not only that, we have like a really explicit description, right? These Ti stars. Okay, so basically this gives us a good enough grasp so that we can actually get to the very end. And I tried to plan this, but I still ran out of boards. So I'll rub out at least one of these. Okay. So now we get at the end to our stable finiteness result. I guess this is section 4. Okay, so if you start with 2 commuting local homeos on a totally disconnected, locally compact Hausdorff space omega, and you have an invariant subset. This is open subset invariant under T1 and T2. And let me just call GT to be the associated Diaconou-Renaud groupoid. And the first thing, is this is not by us, just by Renaud, is that you get a short exact sequence. C star G sub T restricted to H, C star G sub T, C star G sub T restricted to omega not H, 0. And you have like this map here, and basically the K theory we had before lets us really control this map and kind of know how to use it. And so we got the short exact sequence, we make some assumptions, assume so kind of this interesting looking condition, F plus 1 minus T2 star G, such that F and G are in Cc omega Z. But this intersect with kind of the compactly supported functions on omega with natural with the range in the natural numbers. But this is just 0. I should give this a condition, right? A name, right? Let me call this M. And I call it M because this is like a generalized matrix condition when a similar work was being done on K graphs. There was this matrix condition that was, I think, first defined by Lisa Clark, Astrid and Huffen, and Aidan Sims. This is like a necessary condition you need, okay? And it's like a generalization of the matrix condition. We show it's equivalent to, there's another condition called the co-boundary condition, And in a paper by Tim Renone and Aidan Sims, it's also equivalent to that. So we need to assume that because it's necessary. And then there's some other condition I'll call P. This is some technical condition. And if you want to ask me about it later, you can, but it's just some technical condition. Basically, it's to do with cross products and how finicky they are and how badly behaved they are with, well, how we don't know how they behave with K-theory and things like that, okay? So something to do with that. Okay, so given these conditions, M and P, then if C star of GT restricted to H and C star GT restricted to omega not H are stably finite, then so is the extension. And so somehow we started by wanting to prove this result, something like this. And then along the way, we realized we did all this K-theory stuff. And this ended up just kind of like being an application of the K-theory stuff. So that stuff became the focus, and this became our application at the end. But that's what I wanted to say. So thank you.